All right, in this module, we're going to talk about Fick's first law of diffusion. And I want to start with a question to see how much you might remember about this topic. So I want you to go to the quiz, pause the video, and I want you to see if you can write Fick's first law, and then identify the terms, name them, and see if you can give the units of any terms as well. So see if you can do that, come back, and then we'll start discussing Fick's first law. All right, so let's start talking about Fick's first law. And along the way, you'll see that we'll identify the equation and identify all the terms. The first thing that we want to talk about with Fick's first law is the concept of flux. So we want to look at what flux is. So flux is matter flow, and it's a matter flow rate. So that's going to be units of matter, so either moles or mass, right? Or it could be grams per second. And then that's over a unit cross-sectional area. And so that could be meters squared or other area units. And so therefore the overall units are mole or grams, so moles or mass, and then per second meter squared, or meter squared per second, in terms of that. So let's kind of sketch this out, because that might be an easier way of thinking about it. So let's say we've got some area, right? So this is our, this here is our area, and we'll just call that A. And so we're looking at our cross-sectional area, whatever that is, and we're looking at the mass flow. So this is mass or moles going through that area. Right, so we're looking at how much goes through that area per unit time. So that's what flux is, and that's important because diffusion is all about the transportation of mass, and we want to look at that, and we want to look at the rate, how fast it does it, but we also need to normalize, right? And so that's where the concept of area comes in, because if we have two experiments, right? One with a small sample that has a small cross-sectional area, and one with a large cross-sectional area, if we look at the raw mass or moles per second, then the one with the smaller area is going to have less mass, and the one with the larger area is going to have more mass, just inherently because there's more surface area. So that's why we want to normalize flux, or normalize flow rate by area, and that's where we come up with the idea of flux. And so flux in the simplest form of diffusion then is equal to some constant then multiplied by the driving force for that reaction. And so this is where we get Fick's first law. So let me change pins real quick. So flux, also the unit or the symbol here is typically capital J for flux. And so we have J as in the flux. And what we're going to look for in this form of, when I write this form of Fick's first law, what we're going to do is the flux of species A, whatever that is, in a matrix of B. So we have A is our diffusing species in a matrix of B. So that's what we're looking at in this example. So the flux, the way we're going to write that is the flux of A, and then the superscript is B, and that's going to be equal to, again, like I said, some constant multiplied by our driving force for diffusion. And so in this case, it's actually going to be negative a constant d, and that's has the same symbols This is diffusivity, or the diffusion coefficient of A and B. And you'll see where the negative comes here in a second. And then this is with respect, and then the driving force, like I briefly mentioned in the last module, the driving force for diffusion is going to be the difference in concentration, right? So if we're looking at matrix B, if one area of B has a lot of the species A and the other doesn't, it's going to want to diffuse towards the site that doesn't have a lot of A. And so that is known as the concentration gradient. And so we have the delta, or change in concentration of A, with respect to position X. So this is our concentration gradient. This is the diffusion coefficient, which is a constant in most cases, and then that's equal to the flux. And the negative comes from the fact that, again, like I said, if this is our kind of matrix B, and if there's a lot of species A on this side, it's going to want to diffuse out just like ink and water does, to kind of distribute and have a random concentration throughout. So it's going to want to diffuse this way, and that's known as down the concentration gradient. And so that's where the negative comes into play. So we have a negative there to imply the flux is in that direction. Okay, so let's just kind of go through all these terms. So again, we talked about this. This is the flux of the species A in the matrix B. It has units. The units here, again, are moles or mass. So I'll do kilograms this time, meter squared per second. This D is the diffusion coefficient. And again, that's the diffusion coefficient of species A in matrix B. And I use this symbol for units, and that this term is going to have units of meter squared per second. So that's kind of an unusual unit, but that's what we have. This C here is concentration of A. And that has units of mole or mass per volume, meter cube. And then, like I said, this whole term is known as the concentration gradient. So let me just write that over here. So the difference in concentration over position. And so that's of species A over distance x. And that has units of, again, mole or mass. And then this is actually meter to the fourth in terms of concentration. Because, again, we have units of, so basically we're incorporating the units of concentration with the units of position. So that's where we get the -4 down here. All right, so this, again, is known as Fick's first law. We're talking about what we call steady state diffusion. So the flux doesn't change with time. So the rate is constant. And then our diffusion coefficient in here is a constant. So that's what Fick's first law, and that's kind of the simplest case of diffusion. And so in the next module, we're going to examine this idea of the diffusion coefficient or diffusivity a little bit more. We're going to investigate that idea a little bit more in terms of self-diffusivity. So that's what we'll do next.